Section: Introduction. In this section, we discuss the significant advancements in large language models, LLMs, marked by the release of OpenAI's o1. This development showcases impressive capabilities and emphasizes the potential of scaling chain of thought, COT, and reinforcement learning to improve LLM performance. While many research efforts focus on replicating these advancements, they often limit themselves to mathematical reasoning tasks. The application of o1-like methods in specialized fields, particularly medicine, remains largely unexplored, despite the complex reasoning required in medical diagnoses and decisions. In the medical field, careful deliberation is crucial for reliable outcomes. The medical domain has unique advantages, such as a narrower scope and easier verification compared to general domains. Additionally, medical reasoning parallels real-world applications in finance, law, education, and security, making progress in this area transferable. However, a significant challenge in medical reasoning is the difficulty in verifying the thought process, which often lacks clear steps. To address this, we created 40,000 verifiable medical problems derived from challenging, closed-set medical exam questions. These problems are open-ended and have unique, objective answers, allowing an LLM verifier to check the correctness of solutions. Our approach consists of two stages for enhancing complex medical reasoning. Stage 1. Learning complex reasoning. We develop complex reasoning pathways through strategy-based searches guided by verifier feedback. The LLM starts with an initial COT, and if rejected, it extends the COT using strategies like backtracking and exploration until a correct answer is found. Successful reasoning pathways are then used to fine-tune the LLM, helping it develop complex reasoning skills through iterative reflection. Stage 2. Enhancing complex reasoning with reinforcement learning, RL. After acquiring complex reasoning skills, we refine this ability using RL. Sparse rewards from the verifier guide self-improvement through the proximal policy optimization, PPO, algorithm. This leads to the development of HuatuoGPT-o1, a medical LLM capable of producing long COTs to identify mistakes, explore different strategies, and refine answers. Our experiments show that this method, using only 40,000 data points, results in an 8.5-point improvement on medical benchmarks with an 8 billion parameter model. Furthermore, our 70 billion parameter model outperforms other open-source general and medical-specific LLMs across various medical benchmarks. Our findings indicate that complex reasoning enhances medical problem-solving and improves RL performance compared to standard methods. Our contributions include the first work to advance medical complex reasoning in LLMs using verifiable medical problems and a medical verifier, a two-stage training approach combining search strategies for fine-tuning, and the development of HuatuoGPT-o1, which demonstrates superior performance in complex reasoning. To create verifiable medical problems, we drew inspiration from mathematical problems that allow verification through outcomes. We sourced 192,000 medical multiple-choice exam questions from MedQA USMLE and MedMCQA for their objectivity and accuracy. However, since these questions are closed-set, we needed to ensure they required deeper reasoning and had unique answers. We selected challenging questions by removing those that small LLMs answered correctly and discarded simpler questions. We ensured unique answers by excluding questions with multiple correct options and used another LLM to filter out ambiguous questions. Finally, we reformatted each closed-set question into an open-ended problem and a ground truth answer, resulting in a dataset of 40,000 verifiable medical questions. Section Summary. In this section, we introduce HuatuoGPT-o1, a medical large language model that enhances complex reasoning through a two-stage training approach using 40K verifiable medical problems derived from real-world exam questions. Our method combines strategy-based searches and reinforcement learning, resulting in significant performance improvements on medical benchmarks compared to existing models. Section: Developing Medical Verifier. In this section, we develop a verifier to evaluate the accuracy of model outputs for medical problems. When we present a medical verifiable problem, the model produces a chain of thought and a result. The verifier then checks this result against the correct answer and gives us a simple yes or no feedback. This feedback is crucial for guiding our reasoning and enhancing performance. We utilize GPT-4o as our verifier, using a detailed prompt for validation. Due to the common use of different names in the medical field, traditional exact matching methods are not effective. Our experiments confirm this and show that our LLM-based verifier is reliable. Next, we outline our method for training large language models to handle complex medical reasoning, identify mistakes, and improve answers through deep thinking. Our approach consists of two stages: first, mastering complex reasoning, and second, enhancing this reasoning with reinforcement learning. In the first stage, we focus on learning complex reasoning. We start with a verifiable medical problem, which includes a question and the correct answer. The model generates an initial chain of thought and answer. The verifier checks if this answer is correct. If it is not, we refine the answer using a randomly chosen search strategy from a set of 4 options. These strategies include exploring new paths, backtracking to previous reasoning, verifying the current reasoning and result, and making corrections to the current reasoning. This process continues until we confirm the answer is correct or reach a maximum of 3 attempts, after which we discard the data point if all attempts fail. When we find a successful reasoning trajectory, we reformat it into a clear and natural language process. This helps us avoid rigid structures and makes the reasoning smoother. We then generate a formal response for the question based on this reasoning. For supervised fine-tuning, we create 20,000 data points from our verifiable problem set using GPT-4o. This data is used to fine-tune our models, teaching them to generate complex reasoning followed by a formal response. This fine-tuning encourages the model to think deeply and refine its reasoning before providing an answer. Section Summary. In this section, we describe our method for training large language models, LLMs, to perform complex medical reasoning by iteratively refining answers through a verifier that checks model outputs against ground truth answers. Our approach involves 2 stages: mastering complex reasoning and enhancing it with reinforcement learning, utilizing various search strategies to improve the reasoning process until a correct answer is achieved. Stage 2. Enhance complex reasoning with RL. In this section, we enhance complex reasoning skills using reinforcement learning, RL. While we learned effective reasoning paths in the first stage, these paths may not be the best. Our goal in this stage is to refine the model for improved complex reasoning. Rewards are essential in guiding our RL training. For a given problem and the generated response, we assign a reward of 1 for correct answers, 0 for incorrect ones, and 0 for responses that lack thoughtful reasoning. Additionally, we combine this reward with a measure of divergence between our learned policy and the initial policy, scaled by a coefficient to stabilize training. For our RL approach, we utilize the Proximal Policy Optimization (PPO) algorithm. The fine-tuned model acts as our policy model, and we train it on a set of verifiable medical problems. The policy generates responses, calculates rewards, and updates the model parameters. We created a dataset of 40,000 medical verification examples, splitting it evenly between the first and second stages of training. We also included additional data to improve generalization and incorporated general verification questions from outside the medical domain, ensuring no overlap with evaluation data. Using our method, we train our models, HuatuoGPT-o1 to 8B and HuatuoGPT-o1 to 70B, based on LLAMA 3.1. In the first stage, we fine-tune the models for 3 epochs with a specific learning rate and batch size. In the second stage, we apply PPO with adjusted parameters. We compare our models against general and medical-specific LLMs. Our evaluation includes standard medical benchmarks and some challenging LLM benchmarks. Our results show that while previous medical-specific models excel in traditional benchmarks, they struggle with newer datasets that require stronger reasoning. Our model, HuatuoGPT-o1, performs exceptionally well across all datasets, significantly outperforming the base model and other comparable models. This highlights the effectiveness of our two-stage training strategy, which leverages verifiable medical problems for improved performance. Section Summary. In this section, we enhance complex reasoning skills using reinforcement learning, RL, by refining the model's responses based on rewards assigned for correct and incorrect answers, while also incorporating a KL divergence term to stabilize training. We train our models on a carefully constructed medical verification dataset and demonstrate that our two-stage training strategy significantly improves performance across various medical benchmarks compared to traditional methods. Section: Ablation Study. In this section, we conducted an ablation study on the 8B model to evaluate the effects of complex COT and reinforcement learning, RL. Our findings, summarized in a table, provide several key insights. 1. Ineffectiveness of simple multiple-choice training. We found that training models only on the original medical multiple-choice questions from dataset D, where we used these questions as inputs and the correct answers as outputs, resulted in minimal improvement over the base model. This indicates that simply learning the correct answers does not enhance problem-solving skills. 2. Impact of complex COTs. We explored various types of chain of thought, COT, reasoning. Our results showed that directly learning responses performed the worst, while simple COT offered little advantage. In contrast, complex COT significantly improved performance by an average of 4.3 points, highlighting the value of teaching models to refine their answers through reflection. 3. Complex COT enhances RL. We compared the RL improvements across different COT strategies. Complex COT, which involved longer reasoning paths averaging 712 tokens, provided a notable gain of 3.6 points, compared to 2.6 points for simple COT and 1.1 points for no COT. This suggests that longer reasoning paths offer richer feedback, helping the model find better solutions. 4. PPO outperforms other algorithms. We evaluated various RL algorithms, including DPO and RLOO, using the same reward function. Our comparison revealed that PPO performed the best, followed by RLOO and DPO. The lower performance of DPO likely stems from its off-policy nature, while PPO benefits from value models, despite requiring more memory. Reliability of the verifier. The verifier is essential for guiding path search and RL. We used GPT-4o as the verifier to evaluate model outputs against correct answers. After manually checking 200 scoring instances, we found that GPT-4o achieved 96.5% accuracy in Stage 1 and 94.5% in Stage 2, demonstrating its reliability. In contrast, the exact match method, which checks for correct answers using regular expressions, performed poorly with accuracies of only 70.5% and 74.5% in the respective stages. This underscores the importance of LLM-based verifiers. We also fine-tuned an 8B verifier based on LLAMA 3.1 to 8B with 20,000 scoring samples, achieving over 90% accuracy. Domain compatibility. To test domain compatibility, we applied our method to the Chinese medical field. We created a dataset of 40,000 verifiable Chinese questions from the CMB exam training set and trained HuatuoGPT-o1 to 7BZH using our two-stage approach based on Quen 2.5-7B instruct. Our results showed that HuatuoGPT-o1 to 7BZH outperformed other similar-sized Chinese LLMs, demonstrating the method's adaptability to new domains. Research on O1. Recent studies have explored the roadmap and core techniques of OpenAI's O1, providing insights into its architecture and methods. Extensions like Llama Berry, LLAVA01, O1 Coder, and Marco O1 have investigated O1-like reasoning in various areas, including mathematics and vision language integration. However, these studies have not yet focused on medical or specialized fields. In contrast, Research in medicine emphasizes O1's potential for structured reasoning in healthcare. Additionally, several O1-inspired models, such as DeepSeek R1 Lite Preview, QWQ, and Gemini 2.0 Flash Thinking, have emerged, but most remain closed source, leaving significant opportunities for further exploration of O1's capabilities across different fields. Section Summary. In this section, we conducted an ablation study on the 8B model, revealing that training solely on multiple-choice questions is ineffective, while complex chain of thought, COT, significantly enhances performance and reinforcement learning outcomes. Additionally, we demonstrated the reliability of our verifier, GPT-4o, achieving high accuracy, and confirmed the adaptability of our method to the Chinese medical domain, outperforming other models. Section: Medical LLMs. In this section, we discuss the emergence of medical-specific large language models, LLMs, driven by the success of generalist LLMs. For instance, the MedPALM series has achieved over 60% accuracy on the MedQA benchmark, reportedly outperforming human experts. We identify two main approaches used in previous medical LLMs. 1. Prompting generalist LLMs. This approach uses specific prompts to adapt generalist models for medical tasks. While it is efficient and does not require additional training, it is limited by the original model's capabilities. 2. Further training with medical data. This method involves training LLMs on medical datasets to incorporate medical knowledge. However, it demands substantial computational resources, as seen with Metatron and HuatuoGPT-o1, which used 1.4 billion and 3 billion training tokens, respectively. Our approach focuses on enhancing LLM's medical reasoning abilities, providing a unique solution. We also explore how chain of thought, COT, prompting can improve reasoning in LLMs. However, creating expert-labeled reasoning paths can be expensive, especially for complex issues. While model-generated reasoning paths with external supervision can help, scalability remains a challenge. Reinforcement learning methods that use reward models show promise but often face issues like slow processing and high costs. Furthermore, we note that developing models with reflective abilities, such as critique and self-correction, has been effective in various tasks but is still underexplored in fields like medicine. Although prompting techniques can facilitate self-critical reasoning, they struggle without dependable reward functions, especially in complex areas. Fine-tuning and reinforcement learning can provide solutions but require extensive human input or complex reward systems. Additionally, self-training methods offer a hopeful avenue for fostering self-correction capabilities.